Hi, so this talk is concerned with approximate Bayesian inference for what are called toll data. So situations where we have many observations and where calculating the likelihood is expensive at each iteration of an MCMC algorithm. So the talk will come up with a scheme to somehow carry out inference in such a situation. So the talk is joint with two of my co-authors, Florian from Montreal and Pierre from Paris. And I'd also like to thank ASEMS for hosting the meeting, and in particular Tony for all the work he's done in organising the meeting. Okay, so an outline of the talk. So generally there's two approaches to Bayesian inference for toll data. One is where you partition somehow the data into subsets, look at each subset separately, and then try to combine the results to make some sort of coherent inference. The second approach is a subsampling strategy, and this is the approach that we'll take in this talk. And the main objective is to try to make Metropolis-Hastings more scalable. So the main idea of our talk is to effectively fix the subset sample size, little n, and to in some way focus on subsets that are similar to the full data, especially in terms of how summary statistics of the subsample match summary statistics of the observed data set. So in that way it shares some sort of similarities with the ABC computation. Okay, so a brief summary of Metropolis-Hastings, which the algorithm is based. So yeah, we're in a situation where we have a posterior with capital N observations, and capital N is a potentially very big number. So it's proportional to likelihood times prior, and Metropolis-Hastings transitions from theta k to theta k plus 1 by drawing theta tilde from some proposal density, and then accepting or rejecting that proposal by looking at A, transitioning from theta k to theta tilde, which is 1 or the likelihood ratio, okay, times the prior ratio times the proposal ratio. The problem for toll data is that the likelihood ratio becomes difficult to calculate at every iteration because capital N is big. So the objective of our talk is to see, can we in some way use Metropolis-Hastings without computing the full likelihood at each iteration in order to accept or reject the proposal theta tilde based on a subset of size little n, where little n is much smaller than the full dataset size capital N. So I'll just give a very short literature review focusing on some particular papers that I think are interesting. Yeah, so to begin, let's think about another way to look at the Metropolis-Hastings algorithm. So once again, we draw theta tilde from a proposal. Now let UK be a uniform number. This is the kind of means by which we accept or reject. This is the stochasticity of that. Let eta kn be this event, which we define as is UK, the random number, is it less than 1 or the ratio that we've seen before. So this is all familiar to us. And we then set the next state of the Markov chain, theta k plus 1, to be theta tilde, if this event ekn occurs. Otherwise, we stay where we are. So in this sense, Metropolis-Hastings can be viewed as a statistical hypothesis test. Does ekn occur or not? Now, the question for us to ask is, can we make that decision with subsets of the data, a subset of the data instead of the full data? In other words, is it possible to make the same decision as Metropolis-Hastings, with a large probability, without computing the full likelihood? So in other words, is it possible to make the decision to accept or reject theta tilde based on a subset of little n, subset of size little n? In other words, let's now consider ek of little n as opposed to ek of big N, where we define that to be the set of UK is less than 1 or Now it's going to be the likelihood ratio of the subset instead of the likelihood ratio of the full data set. Okay, so it turns out that several papers have more or less followed this line of thought. So I'd like to point those out to you. One comes with a nice title of Austerity in MCMC Land, Cutting the Metropolis-Hastings Budget. This is by Korattikara et al. 2013. And their rationale is pretty much the idea that do you need to calculate the likelihood for the full data at each iteration in order to make this binary decision whether to accept or reject the Markov chain? And they argue that really you don't. A similar approach by Bardone et al. 2014 and Bardone 2017 effectively tries to improve upon the Austerity in MCMC Land paper. Now, for each of these methods, they're no longer exact in that the Markov chain on the theta k no longer has the posterior distribution for the full data set as its stationary distribution. So it's inexact. So to put a little bit more flesh on the Austerity in MCMC Land paper, they come up with this very nice way to think about this set ek capital N. This is effectively the chance of transitioning from theta k to theta tilde based on the random number uk that you use to make the decision effectively. So you can rewrite this set ek capital N as, well, what we're calling mu naught and mu as defined here. So it's basically just rearranging the set ek from before, just a little bit of algebra to put in this form. So mu naught is this log of uk times prior ratio, proposal ratio. Mu is this kind of average of the log likelihood ratio for the observations in the full data set. Okay, so they want to reduce the computation by instead of using the full data set with size capital N, they now draw replacement n data from y1 up to y star little n. Okay, so they draw n data points with replacement from the data set. And now mu gets replaced as mu tilde of little n. In other words, replacing the log likelihood ratio for the full observation, full data set, with the log likelihood ratio for the subsample. Okay, and now you effectively want to test a null hypothesis, call it h naught n equals to mu naught less than mu tilde n. Okay, so can we make that transition based on mu tilde n instead of mu, versus the alternative that mu is bigger than mu tilde n, mu naught is bigger than mu tilde n. And if mu tilde n is statistically different from mu naught, it turns out they justify this using a t-test, then you make the decision to transition from theta k to theta tilde using mu tilde n instead of mu. And otherwise, you draw more data to gain more confidence to make that decision. So this is how they scale their algorithm effectively. Now, other papers follow the same kind of strategy. So it turns out that they draw more data until a decision which mimics Metropolis-Hastings can be made with a certain level of confidence. So in particular, I point you to this paper by Bardone et al. In 2017. So it improves upon this Austerity in MCMC Land paper that I've just described. It gives you more theoretical guarantees, but it's more computationally expensive to run. Here's the critical point, I think, from our perspective, and this is that the adaptive subset size little n, it tends to capital N, to the full data size, as the chain is close to equilibrium. In other words, when the chain is in its stationary regime, you need to draw subsets of larger and larger size in order to be able to make the decision to transition to the next state. So that means that the scaling tends not to be as useful in the stationary regime, because you tend to end up using most of the data So it really sort of doesn't give you a lot of scaling in this case. So that really sort of motivated us to think about situations where we draw subsets of fixed size, not of adaptive size. So in other words, if we have a fixed computational budget, can we usefully perform Metropolis-Hastings with subsets of a fixed size little n? Now, I'd also like to point out an alternative approach to the subsampling. This is in the line of a divide and conquer approach, and this is the consensus Monte Carlo approach. So what happens here is that you split the data set into let's say S independent batches. So the full data set is partitioned into y1 up to ... ys. And the posterior distribution is proportional to the likelihood of f of yi, each of these batches, times p of theta to the power of 1 over s. And this is assuming that our data are IID. So right, if you do it in this way, then you can generate S independent Markov chains in parallel, which is an advantage of this approach. Okay, so you look at n of the n, let's call them like batched posteriors maybe. So pi of theta given the batch ys, proportional to the likelihood of yi, times p of theta, the prior, to the power of 1 over s, where I varies from 1 up to s. Process each of those individually, and then derive a weighted average of the S chains. This is the divide and conquer approach. So it's the average of yi, sum those up, divide by 1 over, times the sum of yi theta k. So it's a weighted average. And the wi's, how do you choose them? Well, in the case where the data is Gaussian, the wi's effectively turn out to be the covariance of this, let's call it this batch posterior. And so everything is fine when pi is Gaussian, and this is why this approach is justified. But in the case where you've non-Gaussian, a non-Gaussian posterior, it's not so clear how this method can be justified, nor how you actually choose these yi's to make it work. So I think it's pretty much kind of only justifiable in the case where pi is Gaussian. Non-Gaussian situations, it's not so clear how this thing works really, I think. So yeah, so just to quickly talk about some other exact methods. These are MCMC methods that produce pi of theta given the full observation set as an invariant distribution. One approach using pseudo-marginal MCMC, and there's some papers along that line. In particular, point you out to this exact Sub-Sampling MCMC by Kiros et al. And Jasa. It looks a very interesting approach, and well worth further study, I think. And some others that I'd like to point you out to. Okay. That all said, let's move on now to the approach that we follow in this work. So we're going to begin by looking at the case where the target distribution is from the exponential family, before moving on to non-exponential family situations. Okay, so let's look at what we call sub-posterior distributions. So let's make a definition. Let y of u be a subset of y1 up to n, of our full observation set, and let y u be a subset of size little n, and let pi bar n be a scaled sub-posterior. And let's define that as pi bar n of theta given the subset yu, proportional to the likelihood of yu, to the power of capital N over little n. Capital N, of course, being the full data set size, little n being the subset size, times the prior. So, we get a nice result in this case. So, assume that f belongs to the exponential family, so that the likelihood looks like phi of theta times e of phi of theta times s of y. So s of y is sufficient for the model in this case. And let's make a definition now. So for any subset U, define the set of all possible subsets of this index set 1 up to capital N of size little n. Okay. And define the vector of sufficient statistics between the whole data set and the subsample YU as delta n of U as the sum from 1 up to n of S of yk minus this scaled sufficient statistic for the subsampled observations. So we get an optimality result in this case. So let the Kullback-Leibler divergence between pi and pi tilde, it's defined as so, in the usual way. Then we get a nice result, which tells us that for any U in our set of subsets of size little n, we have that the Kullback-Leibler between pi and pi bar n, which is a sub-posterior for the subset YU, is less than some set by of U, where by of U looks like, well, this log of this expectation defined here, but it's defined in terms of the norm of delta n of U. So the point is that when delta n of U gets very, very small, Kullback-Leibler gets small too. And we can show that for any subset U, such that delta n equals to 0, okay, then pi equals pi bar. Okay. So in other words, if the distance between the subsample and the scale subsample and the for the summary statistics, sufficient statistics rather, and the sufficient statistics for the observed data set go to 0, then you lose no information in make an inference on pi bar n instead of pi, which is a really useful result. And we also have a nice kind of ordering on the subsets. If delta n of U1 is smaller in distance to delta n of U2, then by of U1 is less than by of U2. So in other words, the smaller the distance, the better, the closer pi bar n is to pi. So let's see an illustration of this. This is for a Probit model example. So here we've simulated 10,000 observations, and the Probit model is defined as xk comes from a normal centered at theta with variance of 1, and then we get yk from xk by thresholding it, by thresholding xk at 0. So this turns xk into a binary yk. And the posterior distribution for pi theta of y1 up to capital N, proportional to prior, times 1 minus alpha theta to the power of n, times alpha theta divided by 1 minus alpha theta to the sum of the yks. Okay. So we can put together our scale sub-posterior in this case, and it looks like so. Okay, notice that we have the scaling factor here, times the sum of the yks, where the yks are in the yks in the subset. Okay. So here alpha k is this kind of thresholded probability that xk is greater than 0, given that xk comes from this normal theta 1 distribution. So here we define our delta n of u, our kind of distance between the sufficient statistics, as the sum of the yks, 1 up to n, minus the scaled yks, where k sums over u. And here note that the sum of the yks is a sufficient statistic. And this sufficient statistic is effectively just the number of ones in the data set. Okay, let's see how it looks. So here we've taken a subset of size little n. And what you see in this picture is that the black curve is the true posterior. Okay, and what you see is that as the subsets have bigger distance, so this purple color corresponds to the case where delta n of u is very big, actually, 600 and something in this case. So you get really disastrous inference in this case because the subset doesn't match the full data set in terms of its sufficient statistics. So you just get a really horrible inference. In the green situation, we're doing a little bit better, and you can see still we're really far away from the true posterior. And you see when you get closer, okay, the blue and the red, you're starting to match the posterior more and more. So this is illustrating the previous proposition in the two corollaries. When the subset size is smaller as measured by this delta n, we get closer to the posterior. And in a situation where we get a subset where we get an exact this norm of delta n of u equals to 0, then we get an exact match with the posterior. So it's quite a kind of reassuring result for the exponential family case. In the case where n is 1,000, well, of course, subsamples are bigger in this case, and we do an awful lot better. And again, you see the situation where, in this case, the blue curve corresponds to a subsample where this delta n of u is 4, so it's quite small relatively. We get a really good match with the true posterior. And again, when we're quite far away, we get worse inference with the green curve and with the purple curve, let's say. So let's now think about how to generalize this result beyond the exponential family case. And the main idea is that in the exponential family case, we appeal to sufficient statistics. When we're no longer in the exponential family case, we turn sufficient statistics into summary statistics and try to do something meaningful in that situation. Okay, so now we're in a situation where our data likelihood is, so it's any likelihood model, and the data are potentially no longer independent. So we'll make a definition. We let S be a mapping from the data onto S, where S is summary statistics, and as before, delta n of u is now some kind of distance, some kind of vector of summary statistics for the observation minus scaled summary statistics for the subsample. So once again, we're moving from sufficient statistics to summary statistics. And now we do something important here. There's an important construction in our algorithm. So for each subset, indexed by u, we assign it a weight. We'll call this weight nu n epsilon of u. So it's a weight assigned to the subset of the data yu, where nu n epsilon of u is proportional to e to the minus epsilon times the norm of delta n of u squared. So this is basically a weight function that says, in the case where epsilon tends to 0, it says that all of these subsets are weighted equally. Okay, so we're not discriminating any subsample from any other. However, when epsilon gets very big, this weight function tends to concentrate on that subsample that is most representative. Okay, most representative in terms of this delta n of u vector. Okay, in terms of the norm of it, more like. So it's a very important construction for us, delta n of u, how we weight the subsamples. Okay, so this is the algorithm that we propose. We call it Inform Subsampling MCMC. So what do? This algorithm produces a chain theta k uk. Theta k is the parameter of the model, and uk is the subsample. So a single iteration of the algorithm looks like this. We first of all update or refresh the subset. So we update the subset with proposal from u tilde from some proposal distribution defined on the set of subsamples. And then we accept or reject u tilde. So we set u tilde equal to uk with probability 1 and this exponential of epsilon times this difference of these delta n of uk minus delta n of u tilde. So independently of the theta k chain, we update the subset. And then we update the parameter. In the kind of usual Metropolis-Hastings way, propose theta k from some proposal distribution, set theta tilde equal to theta k plus 1 with probability, call it alpha tilde, where theta transitions to theta tilde with 1 and alpha tilde, etc. Where alpha tilde is now the likelihood ratio of the just proposed subsample, defined at the proposed theta prime and the current theta, and of course the usual prior and proposal ratio too. So once again, kind of 2 steps. Update the subset, and then with that updated subset, update the parameter of the model. So it turns out that our ISS-MCMC algorithm samples a Markov chain on the extended state space, theta I ui. Of course, our primary interest is really in understanding the marginal chain on the theta I parameter. Okay, so in some sense, the ui is almost a nuisance parameter in some ways. So let's denote the distribution of the marginal chain by theta tilde I. So what we're interested here in our theoretical analysis is to quantify the distance in terms of total variation between the target distribution pi and the marginal invariant distribution pi tilde I. So we want to get some kind of handle on how close these two distributions are from each other for a fixed subsample size little n. So let's make some assumptions here. Let's assume that the Metropolis-Hastings transition kernel K, which targets pi, is either uniformly ergodic or geometrically ergodic. So uniformly ergodic is a stronger assumption, and it's saying that the mixing of the chain targeting the actual target distribution pi is fast mixing, so it doesn't depend on the starting point. And geometrically ergodic is a less stringent condition, saying that yes, possibly the mixing of the chain depends on the starting point with a particular mixing rate. We'll make the assumption that the subsets U1 up to U2, etc., are IID under this nu n epsilon measure. Okay, this is how we weight the subsets. And we make an assumption that says that we have some constant gamma n, it's finite, such that for all theta u's, the log of the likelihood for the full data set minus the scaled log likelihood is less than this constant gamma n times capital N times the distance between s of y and s of yu. So let's look at assumption 3 in a bit more detail. So it effectively imposes a condition simultaneously on the likelihood model F and the summary statistics S. So in particular, the summary statistics S of U for any subset U must dominate the likelihood ratio of the exact likelihood over the rescale likelihood. So we'll kind of focus on this assumption again in a few moments, but it's a really important assumption for us. Now, so to continue our theoretical analysis, so we assume that K, the Metropolis-Hastings transition kernel, which leaves pi invariant, is either, well, geometrically ergodic. And in the case where K is geometrically ergodic, we can show that our ISS-MCMC, or Informed Subsampling MCMC, transition kernel which targets pi tilde, admits a stationary distribution which converges to pi as n goes to infinity. So this is good. So it tells us that pi tilde will indeed converge to pi as the subsample size increases. The bad news is that we're not able to obtain a rate of convergence. But in the case where K is uniformly ergodic, so the stronger condition, we can say a bit more than in the geometrically ergodic case. We can show that the ISS-MCMC transition kernel now has a stationary distribution, which again converges to pi as n goes to little n goes to big N. But in this case, we're able to give a specific rate of convergence, so it's a stronger result but admittedly, the situation is a stronger assumption that we're making. So let's think now about the summary statistics. How do we choose those? Well, we can make a few points. So we can say that ideally the choice of the summary statistics, it should guarantee that the subsamples YU, which have a small likelihood, so these would be subsamples that are really not that important to us, that they're assigned a very small weight, so that they really don't kind of enter the analysis as much as subsamples that have a higher likelihood. So in other words, S should be specified in a way that ensures that the likelihood of the subsample goes to 0 at a faster rate than mu n of u, mu n epsilon of u. And if assumption 3 holds, then this will actually hold. Okay, so in situations where you can actually calculate the maximum likelihood estimator for the subsample, where it's quick and easy to evaluate numerically, we recommend setting the summary statistics for the subsample to be the MLE. And in a case where we've got independent observations, using the MLE as our summary statistics is justified, since we've got a result showing that assumption 3 holds in this case. So let's now illustrate the performance of the algorithm on some situations. Right, so a few words on implementing the ISS-MCMC algorithm. So the subset size n, so, how should you choose that? Well, we're not given a very kind of strong answer here, but we essentially say that the choice of little n is related to the computational budget available to the end user. So in the examples that we show you here and the examples in the paper, there's a few more that I'm not going to illustrate that are in the paper itself. We've chosen n to be the square root of capital N. And that gives you some sort of it gives you a substantial computational gain, and it turns out at a price of what seems to be a negligible asymptotic bias. On the sufficient statistics, so as before, we recommend that S should be set to the MLE estimator if it's relatively quick to compute. If it's not, then you're not going to get much scaling from this approach. And the reason that we recommend the MLE estimator is that it's supported by our theoretical results. And in other cases, other sufficient statistics could be used. So I suppose we could appeal here to the ABC literature to suggest for certain models what a good summary statistic should be. So remember we have this eta n of epsilon weighting for the subsets. How do we choose that parameter epsilon? This is really quite difficult actually. This is one that needs kind of careful analysis for each example that one would use. So in practice, epsilon needs to be very large, and if epsilon is very large, it's really the epsilon n, the eta n weighting function would then weight only relatively few subsamples. So getting the chain to mix around those subsamples would be quite difficult, and the algorithm could potentially get stuck in a very small number of subsets. So to avoid such a situation, we suggest that one monitors the refresh rate of subsamples that should occur with probability at least 1%. Right, so our first example. So this is a kind of well-used example that's appeared a lot in the literature. So it's the MNIST database of handwritten digits. Here's an example of some of the data. So the data set consists of 10,000 images of size 16 by 16. Each image belongs to one of 5 classes, the numbers 1, 2, 3, 4 to 5. And these class labels are assumed to be known. So I'm not going to give really any details on this model, but it's some kind of deformable template model. So for the class label equals to I is 1, 2, 3, 4, or 5. The observation is some kind of function of theta I plus some noise term in some way or other. So we end up with, the data set is effectively a noisy set of handwritten images, and the objective is to infer the parameter of the model and to classify the image correctly. So let's assume here that our computational budget is 60 minutes, is an hour. So what we do is compare Metropolis-Hastings to our algorithm, the Inference Subsampling MCMC, with a subset of 100 images. Okay, so 10,000 images in the data set, we're using 100 of them. So epsilon is 10 to the power of 5, so it's big. And our summary statistics are effectively is SI of u, where it's effectively just the number of labels taking the value of I. Okay. How long does it take the Metropolis-Hastings to make a single transition? Well, it takes 41 seconds. The informed subsampling MCMC takes 0.7 of a second, so it takes, you know, quite a couple of orders of magnitude quicker. So let's see a visual illustration of how the algorithm works. So Metropolis-Hastings, after 3 minutes, it's really not recovering any information about the digits at all. Nor after 15, after half an hour, you're starting to see something, and after an hour, you're pretty much kind of recovering the information about what digit is what. For our, apologies for the name here, we should have changed this. This is a previous version of this approach. After 3 minutes, we're already seeing some of the images. 15, we can recover the labels pretty clearly. Likewise, 30 and 60. So you see, for our algorithm, really only after 3 minutes, we're getting a lot of information. We're pretty much recovering what the label is. And to see a visual illustration of objectively how the algorithm performs, let's look at this metric dt. So dt is some metric that we cook up. Theta I star is the maximum a posteriori of model I, maximum posterior parameter value for model I. And theta I L is the estimate of theta I after iteration L. So this tells us with our ISS-MCMC algorithm. So this plot tells us how Metropolis-Hastings does under this measure as a function of time. Okay, and the blue dotted line tells us how the ISS-MCMC algorithm does as a function of time. And what we see is that after 5 or 10 minutes, we're getting quite a low dt score. It doesn't really improve much after that, but the value after 10 minutes is about the same as the value of Metropolis-Hastings after an hour. So we're almost getting, under this metric, as good inference on theta after 10 minutes as Metropolis-Hastings is after 60 minutes. In terms of how we match the posterior distribution, so here is a particular parameter theta I, blue is Metropolis-Hastings, and black is what the ISS-MCMC algorithm says. So it matches the distribution quite well in this case. And similarly for another parameter here. So another example, an AR2 model example. So AR2 model, 3 parameters, theta 1, theta 2, theta 3. The likelihood model here. Okay. And this zeta t, normal 0, theta 3 squared. So so we simulate 10 to the power 6 observations. Okay. And we do our approximate inference with our ISS-MCMC algorithm with n equals to 100 or n equals to 1,000. So we're getting, we're using subsamples of much smaller size than the full data set. And here the subsets are what we might call contiguous windows of the full data set. So we simply kind of window the data to get our subsets. Right, summary statistics. So the summary statistics are effectively the estimates of theta via the Yule-Walker method. And we use a collection of different epsilons. And here, because we have 10 to the 6 observations, sampling the full posterior with Metropolis-Hastings was a really tough task. So it's a situation where it's really useful to do some subsampling to speed up the algorithm. Right, One of the issues we looked at previously was how to choose the summary statistics. In cases where you make a poor choice of summary statistics, it turns out that ISS-MCMC will not do very well. So it's important to point out that limitation. So let's say that you choose a poor summary statistic. Maybe you choose the first 5 coefficients of the autocorrelation function. So what you might do is you might plot the distance between the summary statistics for the full data set and the summary statistics for the subsamples that you visit at each iteration of the Markov chain. And to these we can compare with the log likelihood ratio minus the scale log likelihood ratio for the subset. Remember we had assumption 3 which said that the log likelihood ratio should be less than or equal to some constant times this distance basically. And what we see is that when this distance gets smaller and smaller, the likelihood ratio does not get smaller and smaller. So this tells us that assumption 3 is violated, and indeed when we look at the marginal chains, let's say for a theta 3 parameter, we're not getting very good match to the full posterior. So poorly chosen summary statistics lead to very poor inference. However, when we use the Yule-Walker coefficients as our summary statistics, we now see that assumption 3 is valid. So what we see is that when this distance between the summary statistics and the summary statistics for the observed data, summary statistics for the subsample data, when this distance gets small, okay, we see that the log likelihood for the full data minus the scale log likelihood for the summary statistics also gets small. Okay, so this tells us that assumption 3 is valid, and we see that S is appropriate because once again this log ratio doesn't grow faster than linearly in this distance here. And indeed, when we look at the marginal distributions for theta 3, for the case where n is 1000, remember that capital N is 10 to the power 6. We see that, this is for a couple of independent runs, we're getting very good match to the true posterior distribution. It's a really reassuring result in this case. In terms of the total variation distance between the ISS-MCMC chain and the target distribution, we see that for n equals 1000 for various values of epsilon, so epsilon equals 0 is where we're equally weighting all subsets, so not discriminating any subsets. So effectively, it's not what you do in practice. You see that you get quite far away from the blue, which is the Metropolis-Hastings. Okay, so not useful. We're not weighting subsets at all. Purple, where we have epsilon equals 5 times 10 to the power 6, what we see is that we get pretty good agreement with Metropolis-Hastings. So the pi tilde approximate posterior is close under this total variation distance to the target distribution. And this is plotted as a function of time, and time is on the log scale here. So actually we're getting really good inference after, let's say, 10 seconds compared to 1000 seconds with Metropolis-Hastings. So again, we get pretty good speed up at the cost of a pretty small bias, it turns out. Okay, so just to finish up, our ISS-MCMC scheme, what does it do? Well, it allows the end user to deterministically control the complexity of the Metropolis-Hastings transition. In other words, how costly it is to transition. The key point is that we subsample the data according to their fidelity to the full data set through summary statistics. And we have some results that tell us asymptotically the distance between the sub-posterior distribution and the true posterior. And our paper is recently appeared in Statistics and Computing. You can also find it on the archive. And yeah, if you have any questions or want to follow up in this anyway, just please let me know. So once again, Thanks very much.